In this video, we will learn about elimination reactions that can take place at sp3 or aliphatic carbons. Specifically, the types of reactions we'll be learning about are called kind of E1, E2, or E1CB types of elimination reactions. An elimination reaction can occur when you have a leaving group attached to an sp3 carbon if there's a hydrogen atom that's beta to that leaving group. So for example here, I'm a iodoalkane there. I have two hydrogens right there that are beta to the leaving group, so I can call that alpha and beta, where alpha is the carbon directly attached to the leaving group, beta is the carbon one carbon away from that. And so there I can do a beta elimination to create a new pi bond between the beta carbon and the alpha carbon, and then also expel a leaving group. The three different types of mechanisms by which elimination reactions take place are E1, E2, and E1CB. So what we're going to do is to look at those three mechanisms for explaining this reaction. To be clear, I'm not saying that any one of these is necessarily the correct mechanism for this reaction. I'm just saying that there are three potential mechanisms we can use right now. We'll talk about how to decide which one is the better one later on. So in an E1 reaction, this is analogous to an SN1 reaction, and in an E1 reaction, the leaving group leaves first spontaneously on its own. So the E1 mechanism looks like this. The first step again is that spontaneous leaving of the leaving group, like so, to get you to a carbocation intermediate and the iodide leaving group having already left. At that point, we can do our deprotonation. So our base will come in, deprotonate. That then leads to the pi bond formation between those two carbons. This process involves two mechanistic steps, and generally what we see is that this first step is the slow step. And that should make sense because it should require a lot of energy to just spontaneously break apart this carbon-iodine bond to get to two ions. So this is generally our slow and rate-determining step. The second step, in which we form the pi bond, that should be very fast, because we're going from a high energy intermediate here down to a lower energy, I guess in this case it's a product. And so because of this, we can write our rate laws like this. The rate of this overall reaction only really depends on the initial electrophile. And that's because, again, the rate determining step only involves the alkane here. It does not involve the nucleophile or the base. The second common type of elimination mechanism is an E2 mechanism. And so in an E2 reaction, what we get is that both the leaving group leaving and the deprotonation and pi bond formation all happen simultaneously. So the mechanism looks like so. So given the exact same reaction, we would have our base come in, deprotonate. That would collapse down this pair of electrons to form a pi bond that then expels the leaving group all simultaneously. Because this is all happening at once, there's only a single mechanistic step here, and the rate of the reaction then is dependent on all the pieces that are colliding, which are the base and the electrophile. The final type of elimination mechanism or reaction is an E1CB reaction. In this one, what we get is actually the deprotonation is the fast step, and the subsequent elimination and departure of the leaving group are the slow steps. And so the mechanism looks like this. So we would anticipate in an E1CB mechanism that we get first deprotonation, and rather than forming a pi bond right away, this pair of electrons instead just ends up as a carbanion in a carbanion intermediate. This carbanion intermediate, after some point in time, then can collapse, kick out the leaving group to form the pi bond. In E1CB reactions, the rate determining step is not always clear. Sometimes it's the first deprotonation step, sometimes it's the second kind of elimination step. Either way, what we need to recognize is that the carbanion formation is the key part of this reaction that distinguishes it from E2 and E1. And so of course the question should come up then, well, given that elimination reaction, how can I predict whether I should be drawing an E1, E2, or E1CB mechanism? And the answer in some ways is pretty clear, in some ways is a little more complicated. I think something important to understand is that these elimination reactions are always going to be somewhere on a spectrum. They're never purely E1, purely E2, or purely E1CB. We're always kind of somewhere along this range. nonetheless, we can have some general guidelines. So in general, what we'll see is that when we have really strong bases, E2 and E1CB reactions will be favored. And usually E1 reactions are going to only be taking place or observed if we're dealing with a pretty weak base. So for example, if I give you these two contrasting reactions here, I would notice that here I don't have any strong base. So the most nucleophilic species is ethanol, and that ethanol is neutral. Compared to over here, I have sodium ethoxide, which is going to be a negatively charged species, so a pretty strong base. And so if I'm guessing, at least, I'm going to guess that on the left here I have likely an E1 process. On the right, I likely have an E2 process. And so if we're thinking about the E1 reaction, the key step, or the rate determining step, was to make a carbocation. And so naturally, it should make sense that structures that can stabilize a carbocation are going to be a little bit better at doing an E1 reaction. So for example, here I have a situation where if the bromine were to leave spontaneously, I would have a stabilized benzylic carbocation, versus here I would have a primary carbocation. And so what that means is that likely I would have an E1 reaction in the first case, and almost no reaction in the second case, because an E1 mechanism would be too hard, and I don't really have a strong enough base to do an E2 reaction. Conversely, for an E1CB reaction, the mechanism goes through a carbanion intermediate, and so in order for the reaction to go faster, we should anticipate that a stabilized carbanion is going to lead to a faster reaction rate. So in our structure, we'll want to look for things that stabilize negative charge. And for example, here I have an electron withdrawing group in the aldehyde, such that if I deprotonate at this position, I'll have a lone pair of electrons stabilized by resonance. Whereas if I try to deprotonate here, for example, I don't have that stabilization. And so what I would guess here is that I'd likely have an E1CB reaction in the first case. And here, because I have a strong base, I'm going to have an E2 reaction most likely. Finally, we can also consider that in an E1 reaction, the only thing in the rate law is the molecule that contains the leaving group. And so what that means is that we really need a good leaving group for an E1 reaction to go kind of at a fast rate. And so what we would see, for example, here is that we have a triflate versus a chloride. And so in terms of leaving groups, at least, a triflate is a better leaving group than a chloride. And so we would expect, relatively speaking, to have a fast E1 in the triflate case and a slow E1 in the chloride case. Elimination reactions do exhibit some forms of selectivity, so we'll go through those now. The first one that we'll consider is that elimination in an E2 reaction must take place in an anti-periplanar or anti-coplanar fashion. When I say must, I mean that it is much more favorable for an anti-periplanar or anti-coplanar reaction to take place versus the syn-periplanar or syn-coplanar reaction. So let's go through what those look like. In an anti-periplanar reaction, we have the proton that's being deprotonated completely anti to the leaving group that is leaving. And if we think about that in terms of a Newman projection, what we can see is that, I'm going to draw up all my structures here. Our structure looks like this, right? And the plane of the reaction that we're considering is the hydrogen and the leaving group there, and in the side drawing here, like so. Let me pull up the syn-periplanar situation as well, just to give us the comparison. So syn-periplanar can be kind of drawn out all this way. Again, I'm going to highlight the plane in which that reaction is taking place. So I have the syn orientation of the hydrogen and the leaving group. So to understand this preference for the anti-periplanar reaction, we have to think about the orbitals that are involved. So if we're trying to break this carbon-bromine bond, that means that we're putting electron density into the sigma antibonding molecular orbital corresponding to that bond. And that antibonding orbital, of course, is oriented to be in this direction, so opposite and away from the carbon-bromine bond itself. And what you can see in this case is that I have this nicely lined up such that I can do my elimination reaction like so. So the CH bond is parallel to the sigma star antibonding orbital. In the syn-periplanar case, I have to do the same thing. I need that pair of electrons in the carbon-hydrogen bond to be able to kind of go into the sigma antibonding orbital. But what you see is that the majority of the orbital volume for overlap is now not aligned with the electron density of this sigma bond here. Rather, we only get this kind of smaller tail end of that orbital. And so whatever overlap is possible is very small, and so that makes the syn periplanar process very unlikely. It's not impossible. So there are situations where we can force the molecule to only have a syn geometry between the hydrogen and the leaving group. And in those cases, the E2 reaction does take place syn periplanar, but that's only because it's not able to take place anti-periplanar. The impact of this selectivity for the anti-periplanar reaction is that only one of the two stereoisomers of the possible alkenes will be formed. Another consideration is which of the hydrogens is actually deprotonated, because if you look back carefully to the examples I gave you, there are situations in which, depending on which proton is deprotonated during the elimination reaction, a different product will be formed. It turns out that in general, what we will try to follow is Zaitsev's rule for E1 reactions, and Zaitsev's rule tells us that more substituted alkenes are the preferred product. And so this may seem at odds with what we've learned in the past about alkenes that are more substituted being more reactive. And the reason that we do follow Zaitsev's rule here, where we're trying to make supposedly the more stable alkene, is that we have to remember what the meaning of more reactive is. More substituted alkenes have higher energy pi bonds, but overall as a molecule are more stable. And so that's the difference. Here in Zaitsev's rule, what we're considering is that overall the molecule as a product is more stable, even though the pi bond itself is higher in energy. The reason the molecule itself overall is more stable is because of hyperconjugation from the alkyl groups to the empty pi star LUMO orbital. So here's an example of Zaitsev's rule in action. So if I take 2-methyl cyclohexanol and I expose it to acidic conditions, the reaction will go through a protonation of the alcohol to create a decent leaving group. That leaving group will leave to make a carbocation intermediate. That can either be eliminated from the tertiary CH bond here or from the secondary one down here. Zaitsev's rule tells us we should do the tertiary one to get to the more substituted alkene versus the less substituted one. And this reaction is a nice example of the fact that we can still get some amount of rearrangement. So there was, in this particular experiment, a 3% rearranged product formed. E2 reactions also will follow Zaitsev's rule, but there's an additional qualification to that, which is that the sterics of the base can make it so that we don't follow Zaitsev's rule. So if sterics are not a concern in an E2 reaction, we follow Zaitsev's rule, same type of product. But if we use a base that's really big and sterically bulky, then you can imagine that it would be harder for the base to deprotonate a hydrogen that's also on a more substituted carbon. And so in that case, we start to see the selectivity go the other direction. This change in selectivity is called the Hoffman rule for sterically hindered bases in an E2 reaction. And so if we do this reaction, we should see that with a relatively smaller base, so ethoxide for example, we get the Zaitsev product. If we switch to the sterically larger base, tert butoxide, we get an inversion of the yield in the alkenes. So what we're getting is a favoring of the Hoffman product over the Zaitsev product with a sterically hindered base. Beyond these features of elimination reactions, considerations involving solvent, etc. are the same as they are for substitution reactions. So having seen SN1, SN2, E1, E2, and E1CB reactions, the question should come up, well, it looks like the reactants are always the same. There's always a base or a nucleophile and some sort of an alkyl leaving group. So how do I pick, given a reaction, which of those mechanisms is most likely, thus allowing me to then determine which product is most likely? And so there's a lot of factors, of course, that we've talked about. And what I'm going to do here is to try to distill those down into the simplest pieces. So we'll start off with thinking about the structure of the two reactants, and this is always where I start to think when I look at a reaction. So I'm going to always look for what's the electrophile, what's the nucleophile, and then I'm going to categorize the nucleophile by one of these 4 categories, and the electrophile by one of these, 6 different categories here. So I'm going to go through this table here by the electrophile side of things. So if I'm looking at the leaving group, the simplest case is I could have a methyl attached to the leaving group. And in this case, the reactions are fairly simple. It's not possible to do any eliminations because there's no beta hydrogen. And so either we do substitution or nothing at all. And if we're going to do substitution, we're going to do the SN2 substitution because forming a primary or methyl carbocation is very unlikely. So SN2 is definitely favored in all cases. Then what I see is a slight shift in the mechanistic preference. So if the nucleophile is not strong enough, I still don't get any reaction at all. If the nucleophile starts to be strong enough, then I will get an SN2 reaction, so substitution directly at this carbon. And finally, if I go to a hindered base, I'm going to get an E2 reaction. This should make some sort of sense because the carbon here is relatively still not that hindered, so substitution is still generally a good reaction to do here. If I still have a primary leaving group, but I have some amount of steric hindrance, kind of one carbon away from that primary leaving group, I get another shift in my reaction preferences, and that would be such that the SN2 reaction starts to slow down enough such that the E2 reaction starts to be competitive if the base is a strong enough base. Right? So here SN2 is still faster than E2, but here once the strength of the base is increased sufficiently, E2 is faster than SN2, and so our major product will be the E2 product. Of course, with the hindered base, that is still the case. As the steric hindrance in our electrophile starts to increase, we start to see the appearance of the SN1 and E1 mechanisms. And so if we have very weak nucleophile, which thus is a very weak base, what we'll see is actually SN1 and a very slow E1 process. So it's hard to say that there's only SN1 going on here, so we're always going to throw in this E1 process as well. As the base starts to increase in strength, we'll start to see the SN2 and then again the E2 type of mechanism starting to go faster and faster. As our leaving group gets even more sterically hindered, we make SN2 basically impossible. So for a tertiary leaving group, we do not see SN2 reactions happening essentially at all. What we will see, however, are either SN1 and E1 in the weaker side of nucleophiles and bases, or what we'll see is an E2 reaction taking place when we have a stronger base. Finally, the time that we will expect to see an E1CB reaction will be if there is this electron withdrawing group that's beta to the leaving group. And so looking at this table might be a little bit overwhelming. There's a lot of different categories and clearly 6 times 4 different entries, but you can draw a few conclusions here. One is certainly that the beta to electron withdrawing group situation is always E1CB. That's the only time we're doing E1CB. Another pattern that we'll see is that if you see a hindered strong base, you should expect to see the E2 reactions taking place. And then finally, we can kind of look for the other patterns. So as long as we're not in a primary leaving group situation and we have a strong base, we're going to have the E2 reactions taking place. And the other thing I try to remember is that if I have weak nucleophiles, so poor and weak nucleophiles, then these are the situations where I have SN1 and E1 reactions. That then leaves me with only everything else I haven't accounted for as an SN2 reaction. These guidelines are, again, guidelines and not hard rules, but these should serve pretty well when trying to predict reactivity given a set of reactants. So that was a table that was looking at the impacts of the structures of the reactants themselves on the rates of SN1, SN2, E1, E2, and E1CB. What we'll do now is to look at some of the external factors in a reaction that might also influence these relative rates. So one thing that we'll see is that polar aprotic solvents will tend to favor SN2 and E2 reactions a little bit more than normal if the reactant, one of the reactant, I guess the nucleophile, has a negative charge on it. This is because polar aprotic solvents don't do a good job of stabilizing negative charge and thus destabilize that reactant. And of course, that should lead to a faster SN2 or E2 rate. On the other hand, polar protic solvents tend to favor SN1 and E1 reactions because the reactants aren't charged and because those polar protic solvents tend to do a good job of stabilizing the carbocation intermediate. A final interesting observation that chemists have made is that depending on the reaction temperature, substitution or elimination might be a little bit favored over the other. So the reason for that is because if we're thinking about the transition states for our reaction, we're supposed to be thinking about this in terms of Gibbs free energy. And that free energy term then has both an enthalpic and an entropic term to it. And as temperature changes, then the relative contribution of the entropy term will matter either more at higher temperatures or less at lower temperatures. And so if you think about a substitution reaction, what we do is we go from having two reactants to having two products. One is the leaving group, one is the substituted product. In an elimination reaction, we go from having two reactants to instead having an alkene as a product, a leaving group, and the conjugate acid of the base. So you have three products. If you're making more products, then that's usually thought of as being a higher entropy situation. And so the logic is that elimination reactions tend to be more entropically favored. And so at higher temperatures, we see that entropy factor become more significant, favoring elimination overall in the Gibbs free energy. So this has been observed experimentally like so. Here's an SN2 versus E2 situation where between 45 and 100 degrees, we can get a 10-ish% change in the extent to which the elimination reaction is favored. Here's an SN1 versus E1 situation where we have the tertiary bromide here and a weak nucleophile. And again, here that change is not massive, but it's still measurable. So going from 25 to 55 degrees for this reaction gets us to an increase in almost 10% yield of the elimination product. So that was a look at elimination reactions, and then also a look at how to determine between substitution, elimination, and specifically the SN1, SN2, E1, E2, and E1CB reactions, which one is more likely.